let's focus more on internal force convection. As I mentioned, most of the questions in P.Eng is from internal force convection. So if you assume that we have an internal flow, so if you consider a control volume, uh, we have an inlet temperature and we have an exit temperature. So the heat transfer, because of the moving of this fluid, is m dot. M dot is mass flow. Cp is heat specific, and temperature difference. The temperature difference between outlet and inlet.
It's a constant temperature, yeah?
Yes, it's a constant temperature. And the surface temperature, we can assume here, the surface temperature is 600 Kelvin. So as the duct is an equilateral triangle, so first we,
Why the temperature of the surface is constant?
yeah, as I mentioned, yeah, you have a small pipe, it's not very small pipe, but it's placed in a molten lead. That one is big and big, very, very big. So the temperature doesn't change. The temperature of the lead doesn't change. So it means that the surface of this duct is in contact with the molten lead and always is at a constant temperature. And it's given, it's 600. So from these data, you can understand this is constant heat, constant surface temperature.
So the question says the lead is outside of the duct and something else, which is liquid sodium, is inside?
Yes.
Oh, okay. That's I thought.
Yeah. Yeah, you can. Yeah, there is a schematic on the right. Yeah, from this schematic, you can see there's a molten
Oh, okay.
here, and we have a liquid sodium. So before going to solve this problem step by step, first we need to find the surface area. So this one is an equilateral triangle. So what we need to do first, we need to find the perimeter. So we have three sides. 3 times 3 centimeter is 0.09 meter. And the length is 4 meter. So we can calculate the surface area. Surface area equals 0.09 meter times 4 is 0.36 cube meter. So first is the convection. It's from the previous session. So it's 1 over convective coefficient and surface area for the inner convection. So we do have both of them. This is for internal convection. For the stainless steel conduction for the duct, we need to know L. L is the thickness of the duct. And the conductivity, this coefficient is given. And just you need to calculate the average area. So be careful how to calculate this average area. So this is for the stainless steel.
A question here, sorry about that.
Yes, no worries.
Why there is a Q maximum here? Why we use C minimum?
So as I mentioned, because the fluid with a minimum specific heat experiences the maximum temperature difference. That's why here we are using C minimum. And the fluid with the maximum C doesn't experience the maximum temperature difference. That's why here we are using C minimum.
Okay, and when we select T in and T those two temperatures, so we have to go and find the maximum delta T, which when it doesn't matter which one is that?
Always the maximum temperature difference is the temperature difference between the inlet of the hot fluid and inlet of the cold fluid. So there are four temperatures. So inlet
Yeah.
and outlet for the hot fluid, inlet and outlet for the cold fluid. The maximum temperature difference is between two inlet temperatures.
About the table, which is when we are using the effectiveness NTU method, the type of the shell and tube, like being co-current or counter-current, is it matter or not?
Yes, in some cases, yeah, it's very important to identify its parallel flow or counter flow because different relations are given for each configuration. So we're gonna review at the end. It's very important to identify them and refer to those tables. Yeah, we have actually a problem that we need to identify the configuration for it's if it is parallel flow or is a counter flow. So we're gonna review together.
Excuse me, I just want to say that in the table 11.4, there is a formula for epsilon when we have n shell passes, 2n, 4n tube passes. But actually, for calculating epsilon, we have to calculate epsilon 1, which has a long formula, and then put it in the another formula. Maybe the formula that you mentioned is actually after simplification of that long formula, we reach to it. And there is actually another table, 11.5,
Yes.
and I think maybe your formula is in that table. But
Yeah.
I have another question that in the graphs there is only two shell passes, shell and tube, and if the number of uh, shell actually is more than two, then we cannot use these graphs.
If only is given, only is available for maximum two shell passes, yeah, it means that you cannot use anymore. If you have more passes, and you should use these relations. Talking about those tables, yeah, there are two tables. One table is defined based on epsilon, and the other table is defined based on the NTU. We're gonna review both tables at the end of this session, and we're gonna actually double check this formula to see if we can find these correlations or not, or where we can find them. Let's finish first these problems, and at the end, yeah, we can review together. We can refer to those tables together and to find those
Okay.
correlations.
Okay,
Sorry,
thank you.
No worries.
sorry, sir. I could find the formula. Thank you.
Okay. For this question, for this example, so both inlet and exit temperature are given, and is asking for the length of the pipe. Any question?
So you calculate the mean temperature. Why you didn't go with the LMTD?
Yeah, we can go with the LMTD as well. So we can use both of them.
But if you go with the LMTD, you get in different numbers, and all of these are different from the table, yeah?
No, we can do the same calculation with the LMTD. Yeah, this one is with the LMTD. We can check together to see if we get the same answer or not.
Okay, yeah, good.